Okay, so we'll make a start, even though we've only got 3 of you here. I think that means we don't have quorum, but luckily this is not a meeting. Success criteria for today. So in today's lesson and over the next couple of lessons, we're going to work on transformations of the sine, cosine, and tangent functions. We're specifically looking at, we'll look at all three, but we'll particularly focus on sine and cosine. They're where the action's at, really, mostly sine and cosine. When you think about practical applications, by practical I mean, in science more so than going down to the Woolworths and working out exactly what the price of 3 cans of baked beans are. Yeah, so the practical applications tend to be sine and cosine for the functions. So there we go. You can see them there. I can recall the types of transformations and their effects. So, and then just to give it away, the effect of translations on trig graphs, describe the effect of dilation on trig graphs, and describe the effect of, oh, wrong word. What word am I missing? I've talked about translations. I've talked about dilations. What's the other transformation that I should have said there? Say it loud, say it proud. Yeah. Describe the effect of reflections on trig graphs. So that's where we're headed. And to be honest, I'm not sure how long it will take us to get through those. If you're really quick, we might get through them all in one lesson, or it might take a couple of lessons. I've got 3 lessons devoted to transformations, including the application of transformations. But if we don't use all 3 lessons on transformations, it'll give us more time to look at real world problems. So I will try and push us, but if I can see you're at breaking point, I'll sort of dial it back a bit. Hi, Ollie. So down the bottom there, I've described the 3 types of transformations, and I'm just talking about a general function at this stage. So we've got translations, dilations, and reflections. And if you might remember, we talk about horizontal effects and vertical effects on a function. So we're talking about, maybe I'll just use that middle part there to say what it looks like. So a horizontal trans, you know what, even though I've got horizontal first, I think I might go with vertical. So look at slide 4 there. A vertical translation has this effect on the parent graph, or the basic graph of f of x, and we add a value like that. So f of x plus b would be a vertical translation. So what effect does that have on the parent graph? So by the parent graph, I mean the basic graph, the graph that we start with, and then transformations are applied to it. So if the effect that's applied to it is plus b, what effect does that have on the function? Sorry? A vertical shift. So in other words, it shifts. Hi, Louis. It doesn't shift Louis. It shifts upward or downward, yeah? Just to spell it out. Upwards if B is positive, which it was more than just easy talking, and downwards if B is negative. So f of x minus 3 would give you a shift downwards. Okay, this is stuff that we did in our functions unit last year, so this is just a recall. Okay, what about a dilation? What does it look like? If f of x is the parent graph, just this middle column, which I haven't spelled out here, so f of x plus b, if I use A to describe the dilation, how would I describe the effect on f of x? Sorry? Yeah, good. So A f of x is a dilation. And what is the effect of a dilation? Yep, you go. It stretches. Is it going to stretch away from the x-axis, or is it going or away from the y-axis? Sorry. Okay. So the keywords are stretches or compressors, and then it's towards, stretches away from or towards the x-axis or the y-axis. Think about the effect of it. The x-coordinate isn't changing, but the y-coordinate, let's just take a equal to 100. The y-coordinate is getting 100 bigger each time. You think it's the y-axis? It is one of those, correct. Okay, let's leave it. Let's come back to it. Think about it. Okay, and reflection. What does it look like if f of x is the parent graph? The reflection is, sorry, you go. Louis? Just that, yep, negative f of x. Okay, and that reflects, turns upside down in this case. Which axis? Reflects about the y-axis, actually reflects about the x-axis. Yeah, because every positive y coordinate would then be a negative y coordinate and vice versa, whereas the x one doesn't change. Okay, so there's the vertical translations, vertical transformations, and the horizontal translations are a bit like this. Okay, really quickly. So f of x plus b. So we are transforming the input to the function. Okay, vertical transformations transform the output of the parent function, and horizontal translations affect the input to the function. So what's the effect of x plus b? Adding b to the input. It is. So the first thing is we have it shifts left or right. If b is positive, does it shift left? So if b is positive, does it shift that way or does it shift that way? Does it shift to the left or shift to the right if b is positive? Yes, well done, Ollie. It shifts to the left. It's kind of counterintuitive to, you normally think of right as being positive and left as being negative. And it's kind of counterintuitive. But if you think of something like the null factor law, where when you solve for x plus b equal to 0, you get x equals negative b, it kind of gives you, that's where the negative b comes from. Okay, so positive b shifts to the left, negative b shifts to the right. To be honest, what I've written is perfectly right, but it almost feels better to write it like that, so that you've got that sort of the sort of idea that it's an opposite value to it's an opposite direction to what you'd think. But f of x plus b is technically how you should really write it. So dilation, same thing, isn't it? Stretch compression. So we're going to explore this. Maybe we can then come back to what it's doing there. A stretch or a compression as well. And a reflection reflects about the y-axis. Okie dokie. So that's a summary of those translations, a very brief one. But what I'm keen to do is really look at the effects of these translations on, or transformations, I should say, on trig graphs. I'm going to look at sine graphs mainly, just because it's probably a bit easier to focus on one and then consider what it would be like for the other ones. And what I'm going to do in turn is I'm going to just look at each of those translations and get you to think about, I'm going to write these on, if I have a whiteboard marker, I do. I'm just going to write this on the side of the board. And what I'm going to ask you to consider is when we apply these transformations, before we actually look at it, we're going to go, what What does that do to the amplitude? What does that do to the period? And finally, what does the graph look like? So what we're getting into here is sketching territory, because ultimately with your graphics calculators in the exam and something like Desmos outside of the exam, the easiest way to draw a sine, cosine, or tan graph that's had transformations applied to it is to put it into your graphics calculator or Desmos and look at it. But there is some benefit, of course, in general to knowing what the effect of the transformations are. So you've got an expectation of what should be drawn. And that means that there's a lot more analysis going on in your head rather than just looking at a picture and then analyzing. And of course, if you are out without a calculator, then there is a lot of benefit to knowing what the transformations are. Plus, you might need to do you might need to work out what a function is based upon a graph. And having a graphing calculator will only allow you to do trial and error to try and capture the graph on your calculator. But you should be able to look at a graph and work out what transformations have been applied to it. So that's what we're going to do there. So each time we're going to have a look at a translation, and we're then going to shift over to Desmos and see it in action. Just in terms of sketching in general, so I'm not very good at sketching, even after all these years. First of all, you need to sort of work out what over what domain you are going, or what interval you're going to be sketching. Like, is it going to be 0 to 2 pi or negative 2 pi to 2 pi, that kind of thing. And then I think for the sine graph, as long as you know the basic shapes, so I'll do that on slide 6. I mean, you've got sine, the basic shape of sine is like that, the basic shape of cosine is like that, and the basic shape of tan is like that. So as long as you sort of know that basic shape, then applying transformations is not too bad, and sketching in general is not too bad. So, I mean, what I tend to do is, like we do, like with most graphs, you work out what the zeros are. This is because this graph has an amplitude, it means it has a definite maximum, a definite minimum. So we work out what those are and where they are. So I don't know. I go through phases of drawing the graph and then putting in the zeros, or sometimes putting in the critical points and then drawing it. So I think I'll do that. So if you remember the unit circle, either in your head or just draw one over here, and this is just going for sine, you'd be sort of going, okay, well, at 0, sine is 0. The next critical point, I guess, is here. So that's at 90 degrees, or pi on 2. Sine is 1. So there's pi on 2. And there's, I'm going to call that 1. And then over here, I've got sine is 0 again, and that's at 180 degrees. That's another pi. And then the next one here is 270 degrees, or 2 pi on 3 pi on 2, sorry. And that's -1. So I'll try to go the same distance downways. And then back again at 2 pi. And then sort of like, if you sort of draw your arc by moving your paper, I'm not very good at this, right? So please forgive me, but you sort of draw your arc through, switch your paper around, and then draw your arc through like that. That's roughly right. You can see I didn't hit it quite right there, but it gives you a roughly okay shape. So that's how you sketch it. Sketch your critical points like so. With your transformations, your critical points, if you don't need to know where it cuts through the x-axis or the y-axis, then you can get away with just drawing a pretend x-axis and y-axis based where it's shifted over, and then drawing it in and then labeling it as you need to. But of course, if you need to work out where the x-intercepts are, then your only choice is really to solve it as an equation. So go sine of x equals 0, and then solve for x over your interval. So that's how the sketching works. So we're not going to. So you'll be doing some sketching and stuff this lesson in the practice, and I just wanted to frame it with that's what we sort of how we go about it, I think. But we're now just going to have a look at. I'll just write it up on the screen, but I'm going to go into Desmos as we go along. So I'm going to be flicking here. So let's have a look at the vertical shift first of all. We're just thinking about the sine graph. And I'm going to try and get you to do just a bit of thinking to start with. So let's just say we've got, I'll use y. Y equals sine of x plus 2. What's that going to do to the amplitude? Will that change the graph's maximum? It's not. Well, it will change the maximum. Will it change how big, how wide the graph is, how tall the graph is, which is what the amplitude is? No. Okay, because there's nothing being changed about the actual output to the function. The input hasn't been changed. Okay, so will it change? What will it do then? What do you think it will do? Shifts it to the right. Okay, what else? Is that it? Everyone agree? Shift it to the left. Shift it up. Anyone want to go for shift it down? This is like a really bad Rocky Horror Show thing. It's just a shift to the left. Sorry. It's going to go up. Okay, so this is Desmos over here. And as you can see here, I've just, I've got it in pi to negative pi, hang on. So I'll just look at sine x plus b here. So here's sine of x, and you can see the function, can I get rid of that? Yep. The function goes from 0 through to pi, down to -1, and then back up to 2 pi, and that's when it starts repeating. So its period is 2 pi with a maximum of 1 and a minimum of -1, and the amplitude is exactly 1. So here's sine of x plus b. So it's green. So red is sine of x. And I'm going to just change b to 2. And there it is there. So it's exactly the same shape. And it's exactly the same amplitude, but the entire graph has been shifted up by 2 units. So you can see that this point here, if I go up 2 units, 1, 2, it's there now. This point here is now 2 units up, and so on. So every single y coordinate has been shifted up by 2 units. So that's what a vertical translation does. It literally shifts it up and down, and it doesn't change the amplitude. And as you can see, here it is from 0 all the way up, down to 0, but down again, and back up to 2 pi. The period is still 2 pi. So there's no change to the period, no change to the amplitude, but the graph has been shifted up by 2 units. And I'm sure you'd appreciate that if I went -2, that's like b is -2, then it's going to be a graph that's shifted down by 2 units. Okay, good with that? So exactly the same graph. In terms of working out the amplitude, you can sort of still see that if I look at the difference between the maximum and the minimum of this function, then it's still 2 units across. So you can still work that out. So there's -1 there, and there's -3 there. Okay, so -1 plus -3 is -4. Divide by 2, you get, no, other way around. So -3 minus -1 is equal to -2 divided by 2 is 1, or -1, but then you take the modulus of it, so it's always positive. So there's definitely an amplitude of 1 there. Okay, any questions on that? All right. So that's a vertical translation. Let's now have a look at a vertical dilation. So remember, a vertical dilation is multiplying the function by value. So let's just keep it simple and say 2 sine of x, like so. Just looking at one transformation at a time here, not combining them yet. So what's that going to do? So we've got sine of x, we've got values going into sine of x, and this time every single value that's output is multiplied by 2. So what's that going to do to our graph? Does it do anything to our amplitude? What's it going to do, Izzy? It's going to double it, you think? Okay, so you think that the distance between the maximum and the minimum is going to be 2 instead of 1? Is that what you're saying? Yeah. Okay. Anyone want to say something else? Nothing wrong with being wrong, by the way. What does multiplying by a negative number do? Can we explore that in a minute? I'll just deal with the positive just to not cut out too many. Sorry, not to have too many variables in what we're doing. Too many changes in what we're doing. That's a good question though. What would a negative do? Anyone else got any other comments? Okay, I did see some shakings of heads too. So let's see. What about period? Is it going to change the period? Do you think that it will either increase or decrease the period? The graph will go over a longer distance or a shorter distance before it starts repeating? No, this is just gut feeling stuff, you know. I don't mind. Yeah, it's what's more than gut feeling in that you can possibly consider the effect it will have. But I'm going to talk about that more in a second. Gut feeling is right at the moment. And then again, what does the graph look like? So if Izzy is right, we should expect to see a sort of almost like a taller graph, really, a stretched out graph, I suppose. Let's have a look. So I'll just make this disappear. At the moment, you can see y equals a sine x. A is equal to 1 up here. So it is blue and red is the parent graph. And now I'm going to stretch A up. Like so. So there we go. You can see that the period of the graph is still 2 pi. So between any length of 0 and 2 pi, the graph repeats itself. Any interval that's 2 pi of length, the graph starts repeating itself. So 0 to 2 pi, and then from 2 pi to 4 pi, etc. It repeats itself. So the period is unchanged. The amplitude has been stretched up. Okay, so that's okay. And we can see that it has been stretched up as far as 2 and then down as far as -2. So that gives us a total length of 4 between 2 and -2, but then we halve it for the amplitude. So the amplitude ends up being 2 again. So the amplitude is 2. So you're spot on, Izzy. Is that okay? All good with that? Okay, so it has stretched away from the x-axis, hasn't it? And have you noticed as well that it still has its x-intercepts at the same spots? It's quite pretty, really, isn't it? So that kind of makes sense, because if sine of x, whatever x is, in this case pi, if sine of pi is 0, then guess what 2 times 0 is? 0 as well. So that's why it doesn't change. But if sine of pi on 2 is equal to 1, and then I double the result, then it kind of makes sense that the maximum value is also going to be double. And if the sine of 3 pi on 2 is negative, oh, that makes me feel seasick. If the sine of negative pi, sine of 3 pi on 2 is -1, then it kind of makes sense when you double it, then it goes down to -2. So I guess what I'm trying to say is, by considering the critical points of the function, you can get a sense of what should be happening to the graph as long as you know the general shape of it. So when I said, what does that do to the amplitude? And I said, gut feeling's fine, and it was. But what you could have done to put some consideration behind it was say, okay, well, I'm doubling every single value. What's it like at the maximum minimum? Well, the maximum is 1, and then it would be 2. And what's it like at the zeros? Or that would still be 0. Okay, so it will give you a sense of what's happening there with the stretch. Now, that's a stretch. What would I need to do to A to make it compress? To squish it. That's right, Holly. So if I grab A and take it back down to 1, it now covers the parent graph. And then if I now bring it down, squishy, squishy. There we go. There's A equal to 1/2. And you can see now it goes as far as 1/2 and then down to 1/2. The period does not change and the zeros do not change. They are still exactly as they have always been. Okay, so it's compressed towards the x-axis, and that fills in that first screen about the stretching and compression. Alrighty, is that okay? All good? Any questions? Now, Ollie did ask a question about what would happen if the value of A was negative, like -2. But what are we doing? What are we adding in there when we add, when we go to negative values of A? It's not just a compression, but it's a reflection as well. Okay, so we're going to explore reflections in a second, Ollie, but hopefully it'll make sense that when I just click on the minus here, it'll change it to -1/2. Flipperoonie. Okay, so it flips around the x-axis. Okay, that's a bit trippy. Okay, so I'll leave it there. So that's it. So basically it stretches, the bigger A is, it stretches, and the closer it is to 0, it compresses. And when it gets to 0, it's a flat line. Okay, and then I guess we've already done this really. So a vertical reflection is like y equals negative sine of x, but I won't do that now because we just did it basically. So and again, think of the critical points. When I make, if sine of x is equal to 0, and then I change the output to -0, guess what -0 is? 0. So the zeros don't change. And if sine of x is equal to 1, what's negative sine of x? -1. If sine of x is equal to -1, what's negative sine of x? +1. So every positive value becomes negative, every negative value becomes positive. Okay, let's look at the horizontals. That's where things get a bit trippy. It's my word for the day. Okay, so y is equal to sine of x plus. Now, what I'm going to do is I'm going to say x plus pi on 6. I can say x plus 1 or x plus 2 or x plus 3, but knowing that our x-axis is sort of broken into pi values, because it's a radian measure. I mean, you can measure against degrees, but typically it's radian measures for the x-axis. Then it kind of makes sense if I give an example which has a radian measure added to it, because like x is an angle. So what I'm doing is I'm adding pi on 6 to my value here. Okay, so I could have said, if I had 0 to 360 on my axis, I could have said sine of x plus, what's pi on 6 again? Yeah, I'm hearing the same voices over and over again. I'm really hoping people are chilling out rather than not understanding. Yeah, so if it was a 0 to 360 axis, but I'm just going to stick with radians, so I think that's the thing you need to be really familiar with. What's it going to do? It's going to what, sorry? Shift the, can you just talk a little bit louder, because I really genuinely can't hear you. It's going to shift left on the x-axis. So yeah, so I'm going to have to look this up because I just can't remember. I think it's called a phase shift when you've got shifts left and right, only with Trig graphs. I have to check that out though, because I can't quite remember. So here's y equals x plus b here, and you can see that what I've done is I've got the values of b shifting between negative pi on pi. So I said x plus pi on 6. I just think, yep, my step is pi on 6, so that's right. So that's a blue color. So there's the standard graph. There's x plus b. If I go up to pi on 6, okay, the blue, it's like DNA or something, doesn't it? The blue is going over to the left there by exactly pi on 6. You can't really see on that graph, I know, but if I zoomed up maybe. There you go. So you can see that what was pi is now 5 pi on 6. What was 0 is negative pi on 6. You can see that the amplitude is not affected. And if I zoom out, you can see that the red line here is 0 to 2 pi, and the blue line, it sort of sits there, but then it kind of finishes just before 2 pi. So it starts just before 0 and finishes just before 2 pi. So the length is, in fact, still 2 pi. So the period is the same, the amplitude is the same, and what does the graph look like? It is shifted to the left for that particular value. And of course, as I continue stepping through pi on 2, I'll see if I can zoom in and get that detail again. As I shift this way, it's just shifting by pi on 6 each time, sorry. Like so. Okay, if I go backwards, it's just shifting in the other direction. Okay, so every time it's just shifting. So again, looking at it in terms of, there we go. We would again look at the amplitude. What would be the effect on the maximum value of sine? Well, the sine is still going to max out at 1 because that's the maximum value of the parent function. So just adding pi on 6 is not going to change it because it doesn't matter what angle I put in, the maximum value of sine is always 1 or negative 1 for a minimum value. It always is. The only way I can make a function which is bigger than 1 is by multiplying sine by something, which is a vertical thing to do, not a horizontal thing. So just adding a value to sine will still contain it within 1 and negative 1. And then when you think about the zeros, well, what used to be what the value of x that used to be a 0 is now pi on 6 further on. So it makes sense that the zeros have shifted. So again, I'll just shift it back to just one shift there. So it makes sense that instead of a 0 being at 0, it has to be at pi on 6 now because that compensates for the fact you're adding pi on 6 to it. Okay, I need to start at negative pi on 6 to get the sign of 0. Okay, so that's probably overdoing it a bit. I apologize for that. So that's a horizontal shift. Let's have a look at a horizontal dilation. So we've got y equals sine of, I don't know, let's just go 2x, like so. This time it makes sense to be talking about doubling rather than, you wouldn't necessarily multiply x by pi on 6. You could do, but in this case, what we're doing is we're scaling the value of the input rather than shifting it by a radian measure. So scaling by a whole number would make sense just for your thinking. Of course, you can scale by any number you want to, including pi on 6. Okay, so what does that do to the amplitude? Nothing, does it? Because we're not changing. Sine still has a maximum of 1 and a minimum of negative 1. We haven't done anything to the function to change that. We're doubling the angle, but it's still going to max out. What are we doing to the period? Anything or nothing? Just first of all, something or nothing? Something? Because what we're doing is that too accelerates the graph, doesn't it? Every single value that you put in is going to be doubled every single time. So we're going to get through every single value twice as fast, right? Which means, Louis, the period is halved. We can see that in action, but it's because we're going through the values twice as fast. So if you have a look at the graph, and I'll just bring this back to 0 so we're not getting too many things together. So this is orange. Sine of AX is orange. So when I increase sine of AX to 2, I wonder if I can just change that color from here. No, I have to configure it. A bit similar colors, but the orange graph has gone through the same period sorry, gone through the same interval, 0 to 2 pi, twice in the time it takes sine to make its leisurely way over to 2 pi. And that kind of makes sense. It's going through twice as fast, but because it's going through twice as fast, it means it's repeating over half the interval. Okay, it starts repeating over half the interval. So in general, I'm going to write this down because it's an important fact. In general, maybe I'll write it on the same screen there. Oh man, sorry guys, I'm writing and you can't see what I'm saying. In general, this is what the period is. 2 pi over modulus, or the absolute value of A. Okay, so if 2 is the period, sorry, if 2 is the value of A, okay, then the period is equal to 2 pi on 2, which is equal to pi. So it repeats every pi instead of every 2 pi. As Louis said, it's halved. It's gone from 2 pi to pi. So if I said sine of 10x, then that would mean the period is x on 5. Sorry, pi on 5. Okay, it'd be 2 pi on 10. Am I making enough sense there to move on? Just ask questions now, because otherwise I'm assuming that you're okay. Sorry if I'm going too slowly. I'm not sure if I am or not. Okay. And what do you think? Well, the opposite is going not to negatives, because that just adds in a reflection. The opposites are going to fractions, aren't they? So if I go to a fraction, again, just have a moment. I won't even ask you to tell me, but just think in your own head, what do you think the effect is going to be? Okay, let's have a look at it. So back to 1, and now I'll go to a half. And you can see that between 0 and 2 pi, I've really only covered half. I've slowed the graph down effectively. I've now got only halfway through my graph, and it hasn't started repeating it. So if I just zoom out, you'll see it goes 0, pi, 2 pi, and then back to 4 pi. So halving it doubles it. And that works as well with that general formula there I've got on Air Sketch. I might do this on the next page so you can sort of see it. So if you've got y equals sine of 0.5 x or half x, then that would be the period is equal to 2 pi on a half, which is 2 pi divided by a half, which is 2 pi times 2, which is equal to 4 pi. So it does work as long as you're okay with that, converting a fraction of a fraction into a division and flipping sort of thing. Just any questions about that? Okay, so using your general understanding of transformations and then applying a little bit of logic, you can sort of get there with your transformations of sine and cosine and tan. The last thing is just looking at a reflection. So that would be like y equals the sine of negative x. Again, what does that do to the amplitude? Not going to change it, is it? What does it do to the period? Nothing. It's not really going to change that either. What does the graph look like? Well, you've got to think about it in terms of maybe thinking of the unit circle. If we've got all students take care, and thinking about where it was negative, it's now going to be positive. Where it was positive, it's going to be negative. It might give you some sense of it. So a positive first quadrant angle would go down to here, etc. Would be negative. So let's have a look at that. Go away orange and hello this black one. So we effectively have it reflecting this way as well. It has reflected about the y-axis, but you can't really tell because of the periodic nature of it. But it is actually flipped that way because it's basically changed quadrant by making it negative. Okay, so that's your transformations in a nutshell. So if I was asked to, I'll just go back to AirSketch. So if I was asked to do something like this, graph y is equal to 2 sine 4x, like so, I would do something like this. I would go amplitude is equal to 2, period is equal to 2 pi on 4, which is equal to pi on 2. And then I would get my graph. And it depends whether I need to know the x, the zeros or not. But if I don't, I can sort of go, you're told as well, sketch between, say, 0 and 2 pi, something like that. So then you can go, okay, well, there's 0, there's 2 pi, there's pi, and there's pi on 2. This is going to be horrible. It's going to go from 2 to negative 2. And so I need to go like that. Oh, that's terrible. I told you I was bad at it. That. Oh, man. That and that. So that was really bad. I was just doing it really quickly. But yeah, so you basically got the sine graph repeated 4 times over 0 to 2 pi, and you've gone between 2 and negative 2. And I reckon with a bit of thinking, it's not too hard to work out what these values here would be as well, which I'll leave as an exercise for you to do. But it's in the middle, right, between 0 and pi on 2, etc. So it's just a matter of working out that middle. Hi, Harrison, welcome. No worries. And then maybe as an exercise for you guys to try, this is straight out off the back here. Let's go to cos y equals cos of x minus pi on 4. How about you have a go at doing that? I'll come around and have a look at you, seeing how you go with it. So there's just the one translation there that you need to account for. You need to remember what the cosine graph looks like, and then draw your translation in. And I'll come around and have a look, and then I'll give you some work to do for the last 15 minutes, and we'll continue with that next lesson.